Well, hello students. So today we are going to start our conversation about energy. So before we delve into it, we have to define it. So how would you define energy? Take a moment and think about that. Think what is energy? What would you say? A pretty simple and operational definition of energy would be the capacity to do damage. So if something has the ability to do more damage, it generally has more energy. So there are two types of energies that we are going to be concerned with, at least initially. Kinetic energy, which is associated with motion. It sounds like kinematics. Kinetic means motion. And potential energy. Now, kinetic energy has an equation. Kinetic energy is equal to 1/2 mv squared. And potential energy for us, sometimes if you look it up online, you'll see it written as U for potential energy. I tend to use PE for potential energy. Both are perfectly acceptable and great. And it's going to be equal to mg times your y coordinate, mgy. So we're going to look at these two and see how to use them in an example problem. Okay, so let's consider you're holding a ball right here, and the velocity of the ball is 0. So we could look at our different types of energies. Now the wonderful thing about energy is that it is a scalar, which means that it does not have direction. So you could think of energy as like energy juice, and we're going to fill up these buckets with energy juice. We don't have to worry about direction, free body diagrams, or vector diagrams with energy, which is helpful and nice. So let's consider kinetic energy first. Remember that kinetic energy is equal to 1/2 mv squared. So in order to solve this, we need to know the mass. So let's take the mass of the ball to be 1 kilogram for this example. So the kinetic energy would be 0. Now we need units here. So the mass is in units of kilograms. Velocity is in units of meters per second, and that whole thing is squared. So a kilogram meters squared over seconds squared is equal to something called a joule, or just J for short. So there are 0 joules of kinetic energy in this ball. Okay. So let's consider potential energy. Now remember, potential energy is equal to mgy, where y is your y coordinate. So it seems kind of arbitrary, and it is. It doesn't matter what you call your 0 as long as you keep it consistent throughout the problem. An easy rule of thumb would be to call the lowest point that your object is going to get your 0 point. It makes your potential energies always positive and nice. So in this case, we have, let's get this. Okay, so in this case, the mass is 1 kilogram. Gravity is 9.8, or about 10 meters per second squared. And y is how high the ball is in meters, so this would be 5 meters. So then this would be 50 joules. All right. So we have 50 joules of energy, of potential energy, so we'll fill that up with 50 joules of our energy juice. Our total energy is just both kinetic and potential energies put together, so that would also be 50. 0 plus 50 is 50. So now let's look at this. We release the ball. So the ball falls 1 meter, because right here is our 4 meter mark, right there. And we want to find our kinetic and potential and total energies. So we have to use our kinematic equations to see how fast is the ball going right there. So we could do our givens. We have acceleration is negative 9.8. And in fact, if we call down the positive way, everything going down will be positive. So it's going to make our math a little nicer because we don't have to worry about all the negatives. So acceleration is 9.8 meters per second squared. The math, we're going to approximate it to 10 for this problem because we used 10 for right here for this answer right there. VI is 0. VF is what we want. Change in X or change in Y is 1 meter, and since we're calling down positive, that's going to be 1 meter. And our change in time is our don't care. So our kinematic equation that does not have time is Vs squared equals Vi squared plus 2a change in Y. And we plug and chug at this point. Vf squared equals 0 squared plus 2 10 times 1. So Vf squared is 20. Vf is equal to square root 20 meters per second. Okay, so from here, we can solve for our kinetic energy. Kinetic energy is 1/2 mv squared. Well, we already have v squared right there, so that's great. So it's 1/2, mass is 1 kilogram, and v squared is 20 meters per second squared, because that's already squared. So then, kinetic energy is 10 joules. All right. So square root of 20 is approximately 4.5 meters per second. So our kinetic energy is about 10 joules. Our potential energy now is mgy. Remember, m is 1, g is 10, y is now 4, so our potential energy will be 40. And our total energy, 10 plus 40, is 50 joules. Okay, so let's do this iteration again. I want you to pause the video and solve for the speed of the ball at this point where the ball has fallen 2 meters now. Okay, welcome back. You should have gotten approximately 6.3 meters per second squared. So our kinetic energy is about 20 joules. Our potential energy is mgh, and since our h is, so now we're at 0 down here, 1 meter, 2 meters, 3 meters, 4 meters, 5 meters. So right here, our potential energy is mgh, or mgy, the y component. So m is 1. 1 times 10 times 3 is 30 joules. And so 20 plus 30 is 50 joules. So are you seeing a pattern here? So kinetic energy is 1/2 mv squared. So 1/2 mv squared is 20. So the question is, how fast will the ball be traveling when it's 1 meter from the ground? You could definitely use kinematic equations, but let's look at it from the energy perspective. So the potential energy here, what do you suppose that will be? 50, 40, 30, 20, 10, or mgy. Mass is 1, g is 10, and y is 1, so that would be 10. The total energy does not change. We call this conservation of energy. As long as there's no outside forces pushing or pulling the ball, the total energy will remain the same. So the conservation of energy says that total energy remains the same. So kinetic energy must be 40. Since kinetic energy is 40, we find our equation right here, and so it's 1/2 mv squared. So we plug in what we know, and we can solve for v. And it's really pretty simple. Energy is wonderful. Okay, so in the next video, we're going to show really this example. We're going to go through why it's so powerful and why this energy concept really helps us solve things very quickly and great. All right, see you soon.